Hello everyone. So my name is Augustin and I'll present you my research work, which is collecting telemetry data from low latency microservices. So the plan of today, introduce myself a little bit, talk about the context, goal, consideration, related work, proposed solution, benchmark, and future work. So I'm a master student in Dorsal Lab in the same lab as Farzam, the first speaker, and we're in Montreal in software engineering department. We do research in collaboration with Ericsson, Sienna, MD officials in various tracks. So we have monitoring, debugging, distributed systems, dynamic static instrumentation, hardware tracing, GPU tracing, runtime validation, scale-up trace analysis and visualization. So when you have big traces and then you want to do analysis across a lot of computers, and trace analysis with machine learning. Let's talk a little bit about my project now. So the context, goals, and consideration. So we have a bunch of microservices, and then we want to collect telemetry data from them. So in my case, I use C microservices, and I let them communicate with each other using 0MQ. And by telemetry data, I mean host metrics. So CPU usage is a good example. Application log, application metrics, and request spans. So I have an example of span there. Considerations now. So we collect telemetry data to analyze them later on, and then we want to do cross-host analysis. So at some point we need to bring everything back together. And some hosts have limited hard drive storage, so you want to be able to have filtering capabilities to record whatever you want to record. So a good example is distributed system where you have a lot of heartbeat messages. So when doing tracing, you want at runtime to disable that, for example, collection, those kind of data. And some applications run on hosts with limited resources. So it's sometimes maybe difficult to install an agent or an observative backend because it might affect the application behavior. And last, live monitoring is not that important in our case. We don't need to collect or analyze data as soon as they are collected. Let's talk about tools now that have been created to help us doing that. The first is LTTng, so it's been there for a while now, and it's very good at tracing low latency programs in general. And how LTTng works is just capture kernel event. Let's suppose you want to compute, you want to add the CPU usage, you can just record all the scheduler events, and then having all the trend running on CPUs, you can exactly compute the CPU usage. So one big advantage of LTTng is that you can change recording rules at runtime. So this is a big plus there. And if we want to record anything having to do with application, we can use the user space tracer. So let's take the example of span, for example. If you have a unit of work, you can just log a message at the beginning and at the end. And later on, post-mortem, doing the analysis, you can just know exactly when your operation started and ended. The problem with this approach is that when we have a lot of microservices that involve in the same request, we need to do context propagation. So we need to, for example, have a trace ID and then pass it along all microservices. And for each microservice, so the span, so the work, you need to generate a span ID, pass it on to other microservices in the chain. And you need to do you need to add more code around this to make it work well, and then be able to track the causal relationships. Let's suppose you want to use LTTng again to collect app metrics. What we can do, let's suppose we want to track the number of requests in the server, You can just log a message every time you have a request, incoming request. And at the end, you just aggregate all those kind of metrics across all the hosts. And another problem you have when doing that is that you have different type of counters. So you have, like, for example, synchronous counters, which are modified by the application logic itself. You have asynchronous counters that are modified in an interval, kind of repeating interval. You have histogram, and when you have generally microservices, you have different teams working on each services, and they might not use the same schema, so you need to kind of at the, I would say, at the company level, standardize how you want to collect everything and how you want to structure the data you collect. So I didn't talk about logs. Logs are straightforward. You just log an LTTng event, and then for every log that you have. LTTng, it's a good start point, but we need to add more code kind of around it to standardize everything out, to collect and aggregate all the data that we have. And OpenTelemetry helps us with that. We kind of standardizing everything, becoming an industry standard, and I will define it now as an observability framework. So it comes with a reference, which is, I would say, company vendor neutral and language neutral. And it has standardize all the data that we collect. So it gives a reference implementation in common language, common programming language, Golang, C, C++, Java, and so on. And a lot of projects have worked around OpenTelemetry ecosystem to kind of support their schemas. So you have telemetry backend like Jaeger, Prometheus that accept OTel schema out of the box. And another cool project, you have a collector. It's an agent that you can run on your machine, and you can specify what are your receivers, how do you want to process the data, and where do you want to export them, and then it will do all that for you. So let's suppose you have a host, you can install a collector on each of your containers, one on the host itself, one per cluster, and then chain them how you want, and then move the data how you want, actually. Here is an example of a span definition. So every data that OpenTelemetry collects, it has a span, a protobuf definition that matches it. Here's an example of a span. They clearly state what you have in a span. You have here, for example, trace ID, span ID, the parent, the start time, end time, and then all this is well explained and documented in their reference. Both of the tools doing that kind of help us doing what we want. So let's look at the way we can combine both to achieve whatever we want to do. So here is a diagram. You can see how we can move data around. So I would say you have two big paths. You can choose to instrument your application yourself without using OpenTelemetry at all, and then try to manage to adapt the data later on to match the hotel reference. So you have your application, you do your instrumentation as you want, and then you send all the data that you collected to LTTng. And when once it's sent to LTTng, you can decide to have it in a remote session, so on another host, or keep it local. After that, since the data you collected are not in OpenTelemetry kind of format, you need to actually adapt them to match the hotel schema so it can be understood by visualization tools later. So an example is that when you have the start and the end of the messages, using the timestamp, when you read the CTF-file, you know the timestamp, so you can rebuild that span, kind of the protobuf yourself that I kind of show later on, and then send them to the collector, which will dispatch them to the telemetry backend later. So we got three different types of telemetry backends. So there are time series database, so to handle metrics. So there's Prometheus and Victoria metrics. So Prometheus is very good when you do live monitoring, so it's very fast. But in our context, if you don't use a remote session, you will have to do everything post-mortem. So telemetrics is good at receiving historical data. So it's do the same thing as Prometheus. They support the same query language, the same query API, but in plus it accepts historical data. You have column stores for logs, so log can be seen as a key, kind of pair of key values, and you have traces databases for span, so Jaeger, Zipkin, and so on. So the other way is to use OpenTelemetry instrumentation. So you use OpenTelemetry APIs to collect telemetry data, and then you have protobuf, you serialize them, and then you set them to LTTng. When it's in LTTng, you don't have to adapt anything after because it's already in the format that telemetry backend already know, and then you just need to send it to the collector, which will dispatch it later. So you can view it this way. You have the application code, you have OpenTelemetry libraries, and instead of sending it to the collector, you send it to the third-party service, which is in our case LTTng. So I propose to use most like the second approach. So you have the first part that you do whenever the application is running, is to collect all data. While collecting the data with OpenTelemetry, you also use LTTng to collect everything happening with the kernel. So you can review the metrics, the host metrics. And later on, post-mortem, when you are done collecting data, you can copy everything to the machine on which you want to do the analysis, and kind of send it to the collector and then run them offline. OpenTelemetry doesn't provide the C API, so I just write a simple wrapper, and then I use that wrapper to trace a simple application that I created. So you have, I have two clients here, but you can have as many as you want. You have a proxy, and then as many as server that you want. So client just do basic requests to the server through the proxy, and then the server has mutual threads. So when you finish tracing the application, use the replay system. So it's a simple Python script that will read all the traces that have been gathered, and then we send it to the collector, which will dispatch it later. So for people who doesn't want to use a lot of tools, you can use Grafana to kind of view all those telemetry data in one place. Around the benchmark, you have all the reference there. And let's talk a bit about the benchmarks. So if I want to measure the overhead of actually recording spans, so doing tracing, recording the spans, all I need to do is start a span and end it right away. So after that, I just measure the time to do the operation. And I tested out a lot of configurations. So you have a lot of categories there. You just need to choose one option per category and then combine them. So with LTTng, I can decide to not run an LTTng session, but having, of course, trace points. Or run the LTTng session, but discard all the events. Run an LTTng session, and then record the UST event, or run a remote session and then record everything. I can decide to instrument my application or not, and I can decide to export the data locally to LTTng, or to a local OpenTelemetry collector, to a remote OpenTelemetry collector too. And I can decide to use simple or batching processor. I will explain the processor later. So this is a lot of combination. I will not show all the results for all this. I will just give a summary of what are interesting that I found. So the simple processor is, when a span is created and then it's ended, it gets sent to a processor, which decides if you want to export the data right now, or you want to batch them. So the SIM processor, what it does when the span ended and it's created, it just sends it to the exporter that you configured in your application. So once span ended, we don't wait. The application kind of business logic stop, it export and then it continue. That's kind of the simple span processor. So when sending data to we can decide to send it to the remote OpenTelemetry collector, to a local session, or to a remote session. So generally using LTTng reduce by like kind of 10 times faster, just because we don't have the network calls. Yeah, the network call, the gRPC call that kind of make everything slow down. That slow down everything. For the batching processor, what I do is that I just export, whenever a kind of a span is ended, I continue my business logic, and then there is a thread that kind of batch all the span that are created and then export them every 5 seconds. And when doing that, since it's run on a different thread, there is not a big difference in time of the mean time to create a span, but it takes just a little bit less uses CPU time while sending everything to LTTng. So I prefer LTTng in this case again because we don't have all the network calls that are done kind of local LTTng that are done by the kind of using sending thing remotely. So this is an experiment that I did too. Is trying to flow the ring buffer, so OpenTelemetry ring buffer. So I just create span back to back, and then trying to flow the ring buffers. So when using the SIM processor, there is no loss because we kind of stop the application logic. We make sure everything is spotted before continuing. But when doing the batch, we could lose event because it's running on a separate thread. So I run it for 1 minute, and then when using OpenTelemetry collector, I lost almost all the events because what happened is that in the OpenTelemetry API, what they do, they export batches one by one on the other thread. And since sending everything remote is take more time, it take more time using gRPC, like more than logging everything locally to the disk. It takes less time using LTTng, and then we get like enough. We don't lose that much event compared to when we send it to the collector. For metrics, so to record the metrics benchmark, we just run our application, a kind of logic without collecting any kind of data, and then we do the same experiment while we measure the time, and then we do the same experiment while exporting the metrics. So I have 4 configurations here. So doing no experimentation at all, running my business logic. The second one is exporting to the collector, to a remote collector. The third one, sending the metrics directly to LTTng session, local LTTng session. And the fourth one is sending everything remotely to a remote session. So LTTng wins again. So it's like 50% faster, 50% less overhead, and in almost all configuration, it's under 1.2% to collect the metrics. Future work, so what I'm working on right now. So as I showed before, when you gathered all the telemetry data and then you have it in CTL file, you need to read them later with a tool, with the kind of script, and then send them to telemetry backend. So this is kind of a long process. So what I'm trying to do is to support those serialized protobufs that are in CTF files directly in trace compass. So what's good about doing that is that when you have both kind of those application telemetry data and the kernel traces, you can join them in analysis and then have kind of some specialized view to view whatever you need to view. So a previous student of our lab, what he did, for example, he recorded all the spans. So it's kind of application telemetry data. And then he has also kernel traces, and then was able to show directly in spans, since he knows in which thread the span was executing, to show directly the thread status in the span directly on the span view. So what this enabled to do is to know exactly on the span when the thread was busy, when he was kind of blocked. So you can effectively know why your requests take longer than usual. And since you have the thread status from all the requests, you can kind of build the critical path between the requests, so the spans. So I'm adding a new analysis to to support those serialized protobufs, to telemetry, OpenTelemetry protobufs, and also a metric view to support OpenTelemetry contests. So let's jump to the conclusion now. So we propose a strategy for collecting telemetry data from low latency microservices. So we benefited both from LTTng speed and filtering capabilities and OpenTelemetry kind of specification to standardize everything out. Total overhead in most of the cases are lower than using OpenTelemetry for both collecting and exporting telemetry data. So that's it. And let me know if you have some questions.
Anybody has a question? Mathieu?
Slide 39?
31.
39.
Okay.
39. No, forward.
39.
Yeah.
Okay.
About the no instrumentation benchmark, I noticed that the duration is kind of close to the duration when there's some tracing going on. So I wonder if you have some, so I suspect that there is some information that needs to be generated even if it's not being sent to a tracer when this is it. Because, for instance, when you use LTTng UST, you can selectively enable the trace points, and there's a macro which is trace point enabled, which you can use to put in your preparatory steps that populate information that would be passed to the trace point. So you can basically, when a trace point is not enabled, you skip the preparation of whatever you would be sending to the trace point. Okay. So I suspect you don't use that.
I don't know that, no.
Because you should. I suspect the no instrumentation number will go way down, because then you can skip all your preparation step.
Okay, I will just my benchmark that. Thank you.
Thank you, Mathieu. Is there any other questions? Yes, Edwin?
What's the meaning of the export delay on the no instrumentation side? What is being exported? Is it like an empty file, an empty string?
Okay, the export delay, you mean export delay? Okay, so what's happening is that, like, when using OpenTelemetry in general, so all the metrics are kind of aggregated and kind of exported every 500 milliseconds or 1 second or 2 seconds, kind of the delay that you want. So when doing no instrumentation, I just discard that kind of export. I just don't do anything at all.
Thank you, Edwin. Other question? All right. Well, it's time for lunch, where we'll be back at 1:30. Before that, I just want to remind you that we have this board there. So we have libside, and tmon. So maybe we can regroup the two libside together, or maybe it's the same, I don't know. If you have other subject, please put it on the board. Just left space between the subjects, we can put plus beside them. And yeah, feel free to put plus on them. So we'll see you in 1 hour and 30 minutes. Thank you.